thanks everyone for coming. Thanks, Shmuel, for asking me to give some colloquium. So, I guess the philosophy of giving a colloquium is that it's supposed to be accessible to everybody, and I sincerely hope that that will be the case. I don't really have a very exciting new theorem to talk about, or, well, there's a theorem that's exciting to me. I'm not going to talk so much about that, but a sort of like, so to speak, a fragment of it, which you may or may not find very interesting. For me, the main reason to give this colloquium is I have, I think, a very easily stated conjecture, which I would be very delighted if someone in the audience or elsewhere were to prove, maybe before the lecture's over. That would be really awesome. Very, very happy to happen. All right. So, what I want to talk about is some interesting to me, new to me, examples of some complex algebraic varieties. In fact, they are literally the complements of curves in C2, which turn out to be K phi 1s. I'd like to know why. This is kind of a bigger story. So, what's a K phi 1? So, a K phi 1 is just, so it's a topological space whose universal cover is contractible. And so hidden in that is that it has a universal cover. Some topological spaces have universal covers that some don't. And there are all these sort of silly expressions like semi-locally simply connected that I'm not even going to try to remember what the definition of them is. So for me, the topological spaces I care about are always going to be homotopic to CW complexes. So, e.g., a manifold, a polyhedron, a complex algebraic variety. These are the only things I'm really going to be interested in. So a topological space, but not just a sort of silly topological space, polyhedron, CW complex, whose universal cover is contractible. And this is equivalent to the homotopic groups are trivial for n not 1. I mean, they could also be trivial for n equals 1, but that's. So, these are the things I want to talk about. So I'm going to give some examples. I'll start by giving some examples. So one example is a point. Universal cover of a point is a point is contractible. Another example, a circle. Universal cover is the line. The line is contractible. And by the way, if G is a group, then we write KG1 if we're at K pi 1 where the pi 1 is G. K pi 1 means a KG1 for some G that I'm not going to specify. So a circle is a K pi 1. Pi, the fundamental group here, is just Z. Circle is KC1. And you have a bunch of K pi 1s, and you sort of take a wedge of them, get a K pi 1. And so another example is a wedge of circles, which, as I'm a topologist, I'm going to draw a picture of that. A bunch of circles all grouping in at some point. This is a K3 group on some number of generators with 1, or I guess n is 3. And since the property of being a K pi 1 is only sort of a homotopic property, anything homotopic to a wedge of one of the many circles is a K pi 1. So another example is complex numbers minus n points. And that's homotopic to this, so that's a K pi 1. So now we're doing algebraic geometry. And I don't want to go into details of what I mean, say a vibration or something. Fiber bundle. If you don't know what that is, think product. Nice example. E could be F times B. If F and B are K pi 1s, then so is. And the proof, you have a vibration, there's a long exact sequence of homotopy groups. And F and B are going to be K pi 1, so their homotopy groups are going to vanish in dimension 1. Homotopy groups of E are wedged in between their homotopy groups, so they all have to vanish. I'll just say long exact sequence. So that's really nice. So you kind of have a few different sort of constructions of K pi 1s. You can kind of glue them together if you're a little bit careful about how you glue them. And maybe I should say this example to be sort of generalized. I told you a circle was a K pi 1. I told you a point was a K pi 1. So I've got a bunch of K pi 1s glued together along a K pi 1. And, you know, if you're a little bit careful, you do a bunch of K pi 1s, and you kind of glue them together, and you're careful that the subspaces you're gluing them along with K pi 1s, and they're kind of including in a nice way. And the kind of, the complex which sort of parameterizes the gluing, you know, so to speak, the nerve of the complex, is itself sort of a K pi 1. Then you get a K pi 1. So we might see an example of that a little bit later on. There are a couple of examples. Gluing things, vibrations. And so this is sort of actually quite powerful because already one nice applications here the pattern says that if you have X variety, every point is contained in a heuristic open neighborhood, which has a complex analytic variety. I think this is a great theorem, which sounds really impressive, but the proof is like somehow really disappointing. But I mean, that's what it's the way in mathematics. And the proof is somehow just, I don't know, by induction of dimension. So you have some variety, and since we only care about heuristic open, let's suppose it's affine, and we just sort of project it to something of lower dimension. And maybe we have to take this point out, but that's fine. We only care about heuristic open. And then, well, this is not quite a fiber bundle, but away from a sort of a heuristic closed set, it is a fiber bundle. The fibers are all just surfaces. The surfaces are sort of surfaces with points missing. And I guess I didn't say so, but every non-compact Riemann surface is homotopic to one of these. So the fibers are all K pi 1. So by induction, this thing of lower dimension, after taking stuff out of it, is a K pi 1 that you sort of done. So that's okay. That's a nice example. Those people who've been taking Frank's class in this room will know that there are nice things called moduli spaces. There are things like moduli spaces of elliptic curves over the complex numbers with some level structure. I'm not going to define what I mean by that. But these moduli spaces are of the form H like gamma. The gamma is some finite index subgroup of ESL2C, and if you take a suitable finite index subgroup, then it acts freely. And these moduli spaces are then the quotient of H, here's the upper half plane, by this nice discrete group, and that exhibits the upper half plane as the universal cover, and the upper half plane is retractable. That's a nice example. Another example, moduli space of, let's say, genus G curves. And I'll say with some level structure. say what I mean by that, but fixing something which is like a little bit of finite extra data. And again, these moduli spaces are going to be the quotient of type space by some group, finite index subgroup of the mapping class group, and type space is contractible. Maybe you know proof of that, maybe not. Another example, you could take the moduli space of principally polarized abelian varieties of some dimension with some level structure, and then the universal cover is single upper half space of some dimension, and that's also contractible. And so I only raise these examples sort of to ask the question, which to me is kind of mysterious. So it's funny that there are these examples of moduli spaces that turn out to be k pi 1, so maybe you have to pass the sort of finite index or overfold covers or whatever. What does it mean for a moduli space to be a k pi 1? I mean, it's not a rhetorical question, it's just a question. Later in the talk, I will give an example, some new examples of moduli spaces that turn out to be k pi 1s. And these are moduli spaces of certain kinds of dynamical systems. And I don't know what it means for them to be k pi 1s. And I know some of them are, and I wonder if all of them are.
I was going to ask, are there examples that are not k pi 1s?
Yeah, let's give an example of a space which is not a k pi 1. Excellent.
Moduli space? Yeah.
Well, I mean, Grassmannians are not typically k pi 1s, right? Like half the infinities are nice. Oh, wait, sorry. Not all Grassmannians. Here's an example, a non-example. Well, all right, let's build up to it. So C2 is definitely a k pi 1. What about C2 minus a line? That's a k pi 1, it's homotopic to a circle. What about C2 minus 2 lines? That's homotopic to a torus. You may not know this. I mean, I have to be a little bit careful. 2 lines in general position. So one way to see this is, so here are my 2 lines in general position. And I sort of start, I take a point at C2, which is on them, and I sort of take some bigger and bigger neighborhoods. And eventually, I kind of intersect these lines, and then I kind of think, well, I've got 2 lines each taken out of a 4-dimensional ball, so that homotopically speaking, this is sort of a wedge of 2 circles. And I can see that in the boundary of the ball, boundary of this B4 is an S3, and these lines intersect this boundary S3 in some knots, and they're unknots. And when I take this thing here, I get a pair of unknots, and S3 minus these unknots, the fundamental group is free on 2 generators. Well, as I kind of enlarge these things, and I cross over this point of intersection, these circles are kind of coming along, and this movie, they sort of bump into each other, and then they close. And maybe you know from algebraic topology, fundamental group of the complement of 2 circles is free on 2 generators. When you push this through here, what you've done is you've killed the commutator. The complement of 2 round length circles in S3. You can think of this as 2 circles of the Hopf vibration. What's left over is a circle bundle over a sphere minus 2 points, which is topologically a circle bundle over, well, homotopically speaking, a circle bundle over a circle. Topologically, it's a torus. So pi 1 is now abelian of 2 generators. So somehow these intersections, when you pass over one of these intersections, what happens topologically is you're attaching a 2 handle, which kills the commutator of 2 elements. Something linking this guy and something linking this guy. All right, so C2 minus 2 lines in general position is sort of a k pi 1. What about C2 minus 3 lines in general position? Well, the same argument says that what I get here, C2 minus this, is homotopic to, well, if I just took that much, it's homotopic to 3 circles. I have 3 circles, and then I attach 3 disks, one for each of these 3 points of intersection, such that this guy kills the commutator of these 2 generators, this guy kills the commutator of these 2 generators, this guy kills the commutator of these two generators. So this is homotopically the 2 skeleton of the 3 torus. And that's not a K pi 1. And the reason is K pi 1s are unique up to homotopy, and so they all have the same homology. And an example of a K pi 1, so the fundamental group here is just abelian Z3, abelian on 3 generators, 3 abelian on 3 generators. All of T3 is an example of a K Z3 one, and it has non-trivial homology in dimension 3. It flows going to 3 manifold. Whereas this is 2-dimensional, so it has no homology in dimension 3. So it's not a K pi 1, so it has non-trivial pi 2. Kind of interesting. There's a homotopically non-trivial map from a sphere to the complement of 3 lines in C2. There's certainly no holomorphic such map. Is there a best map? Is there an analytically interesting map? I don't know. Okay. So my key example, my motivating example, is the following. So we define conf n. This is the configuration space of n distinct unordered points. See? And this is finitely covered by ordered conf n. Configuration space of n distinct ordered points in C, which is to say just C to the n minus the big diagonal. The diagonal where any 2 coordinates are equal. And this covers this by, well, if I have an ordered collection of n distinct points, I forget the order. The covering space, the fiber is sort of, so to speak, a copy of n factorial points with a natural action symmetric. So the nice thing about K pi 1s is if I have a covering space of a K pi 1, it's a K pi 1. Because they have the same universal cover. One is contractible, given only if the other one is. So to show that this is a K pi 1, I just need to show that this is a K pi 1. But this is sort of a much simpler space to analyze, because there's a nice map from ordered configurations of n points to ordered configurations of n minus 1 points. Namely, I just forget the first point, or the last point, but one of them. I have to have them in an order in order to know which specific one I'm going to forget. And the fiber, it's a fibration, and the fiber over a configuration of n minus 1 points is, how can I add an nth point, which is not equal to any of these n minus 1 points? Well, there is the complex numbers minus n minus 1 points ways of doing it. The fiber is C minus n minus 1 points. And that's a K pi 1, and by induction, that's a K pi 1. So that's a K pi 1. Pi, by the way, here is the braid group on n strands. So conf n is a K again 1. And the point is, a loop in this space corresponds to a braid on n strands. And you sort of see a picture. A point in this space is just n distinct points in C. So here's C, here's n distinct points. And as I move around by a loop in this space, these points will just move around. And they kind of braid, and they do something interesting. Who knows exactly what. And at the end, they started at, but I don't know which is which. They're unordered points. Maybe this one switched with that one. That's fine. The same configuration of unordered points. They trace out a braid in time. So the braid group on n strands is the fundamental group of the space.
I might have missed it, but so you're saying there's like an induction, and the base case is ordered configuration for 1 point in C, which is just C.
Very good.
And maybe just more or less last question. Change C to C to D is bigger than 1. It's different.
Yes. That's a good point. I don't want to make my train of thought, but I appreciate that. Thank you. So there's a map actually from Hunt and to sphere, which is much nicer in a way because this is an easier space to think about. So if I have n unordered points, z1 up through zn, we'll just arrange them. I need to order them. But let's suppose we don't know which one is which. We can take that to a polynomial, which is just the product of the right, so this is a monic polynomial, c to the n plus a1 c to the n minus 1 plus dot 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 n. And now these numbers, a1 up through an, give me nice embeddings of, well, so I know this. And so configuration space of n unordered distinct points in Cn certainly maps to a subset of Cn. What subset do I get to? Well, I get exactly the space of monic polynomials of degree n without repeated roots. Okay? So Z Tj distinct if and only if this polynomial, we'll call it f of z, has no repeated roots. And if you have a polynomial, you can test whether it has repeated roots or not by writing down a polynomial in the coefficients of f, the discriminant, which is basically, well, I can look at the difference of the roots, squares, and maybe the product where I is less than j, and maybe there's a sign there, plus or minus 1. I don't really care. This is an expression involving the roots, which is symmetric, vanishes if and only if two of the roots are the same. Since it's symmetric, I could express this in terms of the coefficients of f, which are symmetric polynomials in these roots. And so this is some polynomial, some fixed polynomial, the coefficients of f, which is 0 if and only if we have these repeated roots. So terrible notation, I'm going to use delta to denote both this polynomial and sort of the variety where it's equal to 0. I'm the first person in the world to do this. So conf n is then homeomorphic to c to the n minus delta. So it's the complement of this hypersurface. Okay. Now, let me say a very, very, very slightly different way of stating what it means for a polynomial not to have a repeated root. So f has distinct roots. It's the same thing as saying 0 is not a critical value. Okay, you have a repeated root, so the zeros will come together and the derivative goes to 0. 0 will become a critical value. So let's define, let's let Q be a finite subset of complex numbers. Finite set of complex numbers. And let's define yn Q to be the space of degree n monic polynomials in one complex variable for which no point in Q is a critical value. So for instance, if Q consists only of 0, this is exactly the set conf n. Also, by the way, it's a little bit convenient to sort of cut things down in dimension. If I have a polynomial with distinct roots, I could sort of shift that polynomial by kind of a translation so that the sum of the roots was 0. And translating things that sort of gives you a free action of C on this space. And so portioning out by that free action doesn't change the homotopy type. So just for the sake of cutting the dimension down, let me insist that my polynomials have roots that sum to 0. So these are polynomials sometimes called depressed polynomials. know how they feel. These are the form c to the n plus a2, c to the n minus 2 plus alpha. I can think of this as a sort of a subspace of Cn minus 1, just because Cn minus 1 is twice as easy to understand if you're a real topologist. So monic depressed polynomials. That's just a definition. That's a definition. There's a nice map, by the way, from this space, y and q, to conf n times the size of q. How is that? Well, I have a degree n map from the complex numbers to the complex numbers. Every point in the set Q has exactly n preimages. That's what it means not to be a critical value. So the preimage of F, preimage of Q under F, is a collection of n times cardinality of Q points. So there's an induced map, phi 1 of this space, to phi 1 of this space, which was the braid group on this many things. Here's two conjectures. Conjecture 1, y and q is a k phi 1. Conjecture 2, this map homomorphism. It almost feels silly saying so, but I'll tell you which cases of this conjecture I can prove. So here's the theorem. Y3Q. Okay, right. Roll. By the way, I don't think it's obvious from the definition, but if you're like me, you probably just assumed it was true without actually thinking too hard about it. That these spaces Y n of Q up to homeomorphism should only depend on the cardinality. Well, fortunately, that's true. That Y n Q up to homeomorphism depends only on the cardinality. I don't think it's completely obvious, but anyway, it's true. So there's a corollary of this, which I'll state only because it's something that I personally am a little bit excited about, and it will let me state another conjecture. So there's another kind of modular space that people in dynamical systems like to think about, and the world expert is Laura D'Amato, actually, who's in this room, and these are called the shift locus. So the shift locus is the space. And I guess there's a few different ways to define it, but I'm going to say define it so S sub Q, maybe I should choose a different S sub N, the space of degree n depressed polynomials, depressed monic polynomials, for which a particular, so you think of a polynomial, you can think of it as a map from the complex numbers to itself. So it generates a dynamical system by just iterating that. And so the shift locus are those polynomials for which that dynamical system has a certain property, namely, so such that, and I'm only going to say the words, and if you don't know what these words mean, probably don't have enough time to go into in this talk, such that the Julia set of the polynomial is a Cantor set as the shift. So dynamical systems worlds, the best studied dynamical systems are where you have sequences, one-sided, infinite sequences in a n-letter alphabet, and you act on that space by forgetting the first letter. That's a n-to-1 map called the shift map, and that space is a Cantor set, and we want the action of F and the Julia set to be topologically conjugate to the shift on this Cantor set. So the Cantor set, the Julia set has to be a Cantor set, and this thing has to act as a particular thing. If you know what the Julia set is, great. If you don't know what the Julia set is, I don't want to say geez, but I really don't have time to go into this in this talk. I'll just maybe say as a fact, S2 is the complement of the Mandelbrot set. In one very, so here S2 is an open subset of C1. What open subset is it? It's the complement of the Mandelbrot set. So you may know that the Mandelbrot set is connected. Not only is it connected, but it's sort of, so to speak, full. It doesn't have any, its complement is also connected. So actually the complement of the Mandelbrot set is homotopic to a circle, which is, interestingly enough, KZ1. So here's a fact, theorem. The shift locus is a K pi 1. Well, for what? For n equals 2? Well, I just proved it. It's not obvious, but it's true. N equals 3. N equals 4. So somehow we get 1 for 3. We can prove some theorem about yn k's being K pi 1s. Then it follows almost formally, actually, that the shift locus is a K pi 1 through dimension n plus 1. And the proof of this is, well, there's just an explicit way in which you can build the space Sn by gluing together a bunch of spaces. And the pattern of gluing is a contractible complex. And if you look at what these individual spaces are, they turn out to be homeomorphic to algebraic varieties. They're not holomorphically equivalent, which is interesting because this is a complex analytic space, but they're homeomorphic to certain complex algebraic varieties. And these varieties turn out to be iterated fiber bundles where the base and fibers are just these yn cubes. So if these yn cubes are all K pi 1s, then the pieces you're building this thing out of are K pi 1s, where you're gluing it as sort of a K pi 1, so the big space is a K pi 1. So conjecture, Sn is a K pi 1 roll in. It doesn't quite follow just formally from this conjecture, I just erased from that one, but it's not so far. It's hard to imagine conjecture 1 being false, sorry, being true. Being false. So again, here are some moduli spaces that are K pi 1s. What does this mean? I have no idea. Wish I should have knew.
Could it have to do with some kind of curvature then? We know like not positive spaces with K pi 1s.
That is an exceedingly good question, and actually, it's exactly what I'm just about to talk about. So Amy, who knows a thing or two, in fact, many things, knows that one of the best ways to show that a space is a K pi 1 is to somehow show that it has negative curvature. So there's a theorem, and I forget exactly the names of it. I'm teaching Riemannian geometry at some point. I should remember. I think it's tantalizing. And closed Riemannian manifold. The curvature is non-positive everywhere. Then actually the exponential map, the point universal cover from Rn universal cover. No conjugate, so basically just a nice development. And so in particular, Rn is contractible. That shows the universal cover is contractible. So corollary. And the proof is not really about going out from some point by the exponential map of 1 to p6. The point is really being at some point at damn twiddle and contracting it back to a base point by some canonical path. That's what it means to show something's contractible. For every point, there's a kind of canonical way to contract that down to a point. So it's not really just the geodesics sort of have this nice extension without blah blah, without conjugate points, whatever. It's really that there's sort of a unique shortest path for every point here to the base. And so there's sort of a variation of this curvature property that works in some other kind of nice context. And so there's sort of a generalization of this sort of curvature less than or equal to 0 condition called cat 0. And I'm not going to tell you what this is in full generality, but what I'll tell you is, I'll tell you what it is. So for the special case of, let's say, x, which is going to be a two-dimensional complex built using Euclidean polyhedra, convex Euclidean polyhedra. And what I really want to say is not that x is cat 0, but somehow that the universal cover is cat 0. One says locally cat 0. So I'm going to say locally cat 0. So if I have a Euclidean complex, something I get by gluing flat pieces of paper, that's what Euclidean two-dimensional polyhedra are, it doesn't really matter how I glue them along the edges. I can bend this, but it's still isometric to Euclidean space. There's no kind of curvature. I can glue things along a straight edge. There's no problem. The problem happens where you have a corner. If I glue 3 things and say I have 3 things, each of which maybe has a right angle, and I glue them around a corner, well, what have I done? I've kind of somehow got a point here, a kind of a little cone point. You can see the kind of corner of my little kind of construction here, where I have 3 little angles sized pi over 2, and I glue them together, and at this point has the problem that little circles around it have length r times 3 pi over 2. And to be negatively curved is to have space grow faster than Euclidean space, or not slower anyway. And in this case, it's at least to first order. Second order. This guy is growing slower than Euclidean space to first order. It's terrible. So it has an atom of positive curvature at that point. So what you really want is that at every vertex, you want the link. So the link is made by gluing this sort of a one-dimensional graph. It's a metric graph. And the length of each edge is the angle of the corresponding little corner of your polyhedron. Let's draw an example. I'm gluing sort of a bunch of polyhedra, so Euclidean sort of pieces together. I don't want you to think that these are all flat at the plane, but it's hard to draw it any other way on the plane. And they all have a bunch of little angles. And those angles, if I glue them up, I want to add these angles up, and I want that total length to be at least 2 pi. So the condition is that the length of every vertex, which is a metric graph, in which every loop, every embedded loop, has length at least 2 pi. And if that's true, then the space that you have satisfies the appropriate kind of generalization of negative curvature, so that some analog of the Cartan-Hadamard theorem applies, and the universal cover is contractible and very K-type. So actually, Sn is locally cat 0 equals 2 and 3. Here I think this is a little bit shaky. I don't know if I really believe this, but I would sure like someone to disprove that's false. I think the reason if these things are cat take by runs it's a combination of geometric and bundle and gluing mechanisms. But maybe. So S2 is a K pi 1. Sorry, it's locally tensor, meaning it's homotopic to a complex, which is locally tensor. And the dimensions might have to be bigger than 2.
Alright, what happened to the 4? Erase.
Yes, it is a K pi 1, but I don't know if it's locally cat 0. I know it's made of pieces, which are locally cat 0, and so there's pieces of K pi 1. And because of the way in which they glue together, I know the whole space is a K pi 1. But I don't know, I have to possibly choose different metrics on the pieces to glue them up, and I don't know if locally there's a way to glue the whole thing up. It'd be great if it was. I have no idea. But if it is, or isn't. Okay. So let's do an example. So I'm going to prove special case. I'm going to prove Y3 of 2 points. If I have time, I will prove that this is a K pi 1. This is new, by the way. I mean, I didn't know this. It's true. This is just depressed cubics for which, let's say, 1 and minus 1 are not critical values. What about Y3, 1? Okay, so this is depressed cubics without multiple roots. This is Z cubed plus BZ plus cubed without multiple roots. So delta on 0. What is delta? It's, tell I'm not an algebraist, I need to look up the formula. Minus 4 cubed minus 27 squared. Well, so up to scale, this is basically x squared, x cubed equals y squared. Right? So the place where this vanishes is basically just a cusp. And if you intersect this cusp curve with a little S3, the intersection is a knot. So delta intersect this S3 is a little knot in S3. It's the trefoil knot, actually. And I have a 50% chance of drawing the right one. I think it's this one, actually. I think it's this one. The orientations matter because everything's normal. Pretty sure it's this one. And you may or may not know that the complement of this knot is fired. Actually, there's a Seifert surface. I'm not sure if you can see it. It's sort of made of 2 pieces. So one piece is, roughly speaking, this disc. The other piece is, roughly speaking, this disc that goes on top of it. And this gets glued to this by sort of attaching little twisted bands.
Sorry, can you say for Schmoll what a Seifert surface is?
It's an embedded surface whose boundary is the knot. And this one has genus 1. It's a once punctured torus. And actually, it turns out the complement of this guy is fibered. This is a general sort of phenomenon theorem due to Milnor. When you have these singularities, links to singularities, you get these sort of complements that are fibered. And the fiber is sort of a copy of this surface. And so it's a bundle. This 3-manifold is a bundle over the circle with fiber, the once punctured torus. K pi 1 bundle over a K pi 1, so it's a K pi 1. But it's also a K pi 1 because of curvature reasons. So the fundamental group here, so how do we build this as an actual complex? So this sort of S3 minus the knot, I should say this thing, this Y31 is homotopy equivalent to S3 minus the knot. One way to sort of see it topologically is it's generated by 2 generators A and B with 1 relation. So it's fundamental group. For those of you that know how to compute the fundamental group of a knot complement from like a Wertinger presentation or something, you did an algebraic topology, you know that there's a nice presentation, something like that. And so you could say, well, there's a nice 2 complex actually associated to this presentation, which has, say, 2 loops. And I glue a single disk on it by gluing the boundary to say A, B, A, B, A, inverse, A, inverse, B, inverse. And that 2 complex up to homotopy is in fact the same as this space. That's not the right complex. Turns out I don't think it's true. I think it's false that there's a cat 0 metric on this. Could be wrong. Anyway, there's certainly no obvious cat 0 look to cat 0. So you want to change the complex slightly. This presentation looks pretty good, but somehow make it better, you can add a generator and then another relation without really affecting the homotonic type. It's like adding a cell and then another cell that kind of cancels it out. So you can add ABA equals BAB, and the relation C is AB, I think, A inverse. And then, so that's the same thing as, all right, so AB equals CA equals BC. Still not quite the right complex. Just to be really perverse, we throw in one more generator, one more relation equal to this complex. Very simple. And we could draw a nice complex associated to this, which is the complex. So it's going to have an edge associated to the edge D. It's going to have like a triangle with edges A and B. Have another triangle, edges B and C. And this is supposed to be a three-dimensional picture. So it has another triangle down the back with edges C and A. But it doesn't embed in the plane, so it's a little bit hard to draw. And I'm going to build it in such a way that these triangles are all right angled. Where this is two-dimensional complex where the pieces are clear. I claim this is locally cat zero. There is only one vertex. I just need to look at what the length of it is and check that there's no loops of length less than 2 pi. So while the length intersects each of these edges at 2 points, because each edge runs from that point to itself. So I'm going to get 2 points, 2 vertices for each edge. And I'm going to call that, say, D minus and D plus, depending on whether I kind of intersect it at the start or at the end. So D intersects at 2 points, which are going to call D minus, D plus. And D minus is joined by edges of length pi over 4. A minus, B minus, C minus. And likewise, D plus is joined by edges pi over 4 to A plus, B plus, C plus. What else? Well, A plus is joined to B minus by an edge of length pi over 2. So A plus is joined to B minus by an edge of length pi over 2. And B plus is joined to C minus by an edge of length pi over 2. And C plus is joined to A minus by an edge of length pi over 2. You can check that all the loops have length actually exactly 2 pi, which is bigger than or equal to 2 pi. So this is locally cat zero, so the universal cover is contractible. So this space is a K by 1.
Sorry, Danny. You took 3 triangles, glued them along a single edge.
Yes.
Did you make any other identification?
Yes. For instance, there are 2 edges.
Oh, yes.
Labeled A.
Right.
Those are supposed to be the same edge. Yeah. What do the spaces Y, Q, N look like? Y, N, Q look like? Basically, they look like, well, what's Y, N, 1? The complement of some discriminant. And Y, N, Q is basically the complement of a bunch of translates. This discriminant. This picture is not very literal, except in pretty low dimension. If I say take Y3, 2, that really is, quote unquote, the intersection of these 2 translates of this cut. It's a little bit misleading. The way I drew it, it looks like they intersect in 1 point. They actually intersect in 3 points.
Wait, sorry, it's the complement of something.
It's C2 minus
Right.
the union of these translates of the discriminant. These look like they intersect in 1 point. They actually intersect in 3 points. So the way you get a presentation is, well, for each of these individually, you get a kind of a copy of pi1, which I was writing A, B, C, AB equals BC equals CA. For this one, the complement, I get an XYZ, XY equals YZ equals ZX. Every point of intersection introduces a commutation relation. Remember when I had the two loops that crossed over and became linked, uplink, and we went from free group on two generators to Z2? So the relations are actually that A and X commute, that B and Y commute, and that C and Z commute. And this defines a 2 complex. I'm going to throw in a D and a W, make these all equal to D, make this equal to W. This defines a 2 complex now, and you can look at that 2 complex, and it turns out it's locally at 0. Well, how do you get that 2 complex? You basically just take 2 copies of this, times 2 points, and you glue onto it something. Well, every time you have a square, we have like A and X commute. We can edge from A plus to X plus, a length over 4, from A plus to X minus, from X plus to A minus, and from A plus to X plus, gone one way around. This was X minus. Basically, you add like one of these bipartite. And all the lengths are just pi over 2. And so that makes you a little bit wary because you say, maybe there are now some shortcuts. Like glue, so there's 3 of these things, and I just glue them on. I have a pair of these graphs, and I glue them on. I have one of those graphs for the A, B, C, D. I have an isometric graph where I just change all the labels to X, Y, and Z. And then I attach 3 of these new graphs to that union of 2 graphs, and that's the link of the complex. Well, it looks bad because now there's sort of a shortcut. I can get from X plus to X minus by a path of length pi. Or I can get from A plus to A minus by a path of length pi. But fortunately, A plus and A minus are as far away in this graph as they could possibly be, at distance pi apart. So having another shortcut of length pi still doesn't give you any loops of that. But basically the same reason. I am so out of time, and I'm stuck.
Any questions?
Please.
So, in some of these examples of modular spaces, the groups that you've got, the pies, were often pretty interesting.
Yeah.
Do you have any reason to suspect that in these cases the pies be interesting?
Well, okay, so I had this conjecture that pi1 was sort of actually isomorphic of these blind guys were isomorphic to subgroups of braid groups. When you put them all together, if that conjecture were true, it would tell you something about pi1 of the shift locus. And with some work, that I think is sort of true, I think it would tell you that pi1 of the shift locus is isomorphic to a subgroup of the braid group of the Cantor set. So if you have a polynomial, it gives you a Julia set, which is a Cantor set if it's in the shift locus. If it's in the shift locus, you move around to a loop in the shift locus. This Julia set moves around by some nice motion. This Cantor set moves around and braids in the plane, comes back to itself. Get a map from pi1 of the shift locus to the mapping class group of the plane minus a Cantor set, or like the braid group of the Cantor set. Conjecture, this is injective. So that's true in degree 2 and 3. And maybe in every degree. And it's related to this question. So the groups themselves are kind of interesting. In particular, that would tell you, for instance, that these, well, if you know a group is, if you have a finite dimensional complex whose group is sort of which is a K pi 1, you know that its fundamental group is taller than 3. That's sort of something that you would know. That's true of these. That's true of the braid group, the entire category. Pi 1, whatever. The The mapping class group of the plane minus a Cantor set is the essential quotient of sort of the Cantor braid group. It's circularly ordered, but the Cantor braid group is left ordered. So it has no quotient. Anyway, so that's some weak kind of evidence. Also, you could sort of talk about the homology of these spaces. So a fact which is true is that these shift locuses, their homology vanishes about half the dimension. I don't know if they're Stein manifolds, maybe they are. I don't know if they are with the natural complex analytic structure that they come with as a subset of Cn, but it's true that their homology is what you would expect it to be if you knew that they were sort of Stein manifolds. And from their kind of construction, something about the K-pi1. This homology would be the homology of the groups. Other questions? Has anyone proved the conjectures yet? If you have but are too shy, just see me up there.
I guess for the example you gave, that had a locally homogeneous Riemannian metric of non-positive curvature. The trefoil knot complex is a non-positive curve Riemannian manifold.
Wait, what was the locally homogeneous metric?
Hyperbolic plane cross line, or equivalently, it also has a.
Oh, you're not putting the SL2.
Yes,
that's
two
so
geometry.
cheap. That is so cheap. Yes, you're technically correct. Wait, are you
No, but yes.
Right, technically.
But could that be? That's not a general. That's just a low.
Sorry, what is being a Stein manifold help you with in this
Oh,
world?
if you know your Stein manifold, you know something about the vanishing of homology above half the dimension. Half the real.
So those are stuff.
I don't know if they're Stein or
They
not.
are. They are.
Oh, they are. Well, then that's
So I don't know if that helps your.
that's compatible with the fact that the consequence of being Stein is true enough. Yes.
Okay.
Well, thank you again.